I'd like to welcome Tony Morris from the University of Plymouth. He's going to talk about paleomagnetism. Many of you know Tony because he has been the ESAC chair for the last, I want to say 4 years?
3 years, this is last year, 4th year this year.
Right, okay. Of course, been running the office out of Plymouth, and also Tony has sailed on a very large number of scientific ocean drilling expeditions as well.
Okay, well, hi everyone. It's a pleasure to be able to give this talk to you. And what I want to do in this session is really outline how paleomagnetism might be able to contribute to your drilling proposal that you're working on or might work on in the future. So paleomagnetism is one of the fundamental tools that's available for all expeditions, both the ones that where the science is done at sea and the MSPs, which are where the majority of the scientific analysis is done on land in science parties on shore. I'm not going to try to give you a sort of broad overview of the topic of paleomagnetism. So I'll summarize that on one slide really. So this is a sort of paleomag at a glance, if you like. So some of the things that we really need to just remember while I go through some examples with you. So this topic, this analytical technique relies upon the fact that the Earth has this extraordinary magnetic field, which has got a geometry which is well understood, and in which the direction of the field lines around the Earth varies with latitude. And rocks which are forming through the cooling down of magma, for instance, like in this lava flow, acquire their magnetization as they cool down through the Curie temperature and the blocking temperature of grains in the rock. And in igneous rocks, like lavas, like gabbros, etc., then often the magnetic signal comes from very small crystals of minerals like magnetite, which are perhaps hosted by silicate minerals or might be discrete grains themselves. Whereas sedimentary rocks, as illustrated here in this core being sampled, are acquiring their magnetization as these grains are being deposited in that field, or sometime after deposition, for instance, through the activity of things like magnetotactic bacteria that create magnetite in their bodies as sort of little magnetite grains that help them navigate around in the sediment. So almost every material that we sample through IODP has a magnetic signature. Sometimes that's very weak in the case of really carbonate-rich, pure carbonate sediments, but it's often a very strong signal and easy to detect. So each of the different platform types have facilities for doing paleomagnetic analysis. This is the Paleomagnetic Lab on the JOIDES resolution. The workhorse of these labs is usually a pass-through magnetometer like the one you can see on the right-hand side of this picture, which is capable of taking an archive half-core section and measuring its magnetization and magnetic properties at very small and closely spaced intervals. So throughout all IODP expeditions, that sort of work, that sort of core level analysis is done on the archive half, leaving the working half of the core untouched by magnetic fields, so it can be sampled using discrete samples and can be described by shipboard scientists, etc. So this is the lab on the JOIDES resolution. The CHICU has exactly the same equipment in its lab. The only difference here really is on the CHICU, all of the magnetic lab equipment is inside a shielded room, which has advantages of providing a better low field magnetic environment for doing laboratory analyses. And you can see the pass-through magnetometer on the just to the left of Louise Corneef here, who was working on the Amman cores for the ICDP Amman drilling project some years ago. Well, when it comes to MSPs, then the majority of the analyses, of course, are done on shore, and there are no magnetometers at sea on these expeditions. For the expeditions that have the science party based in Bremen, which is the majority of them, then they use the cryogenic magnetometer that's available in the geo department in Bremen. And here you see Marco Maffioni, who was the paleomagnetist on the Corinth expedition that Lisa was telling you about this morning, analysing samples as part of the onshore science party. Now, there's also a host of other bits of kit that are available that I won't bore you with that allow you to work out magnetic mineralogies, etc. Okay, so what I want to cover in this talk is as follows. I've got 4 topics, and I'll give you an example or 2 in each of these that show you what you can achieve with paleomagnetic methods, so you can be aware of that when you're designing future proposals. The majority of the work that's done on IODP cores is really to establish the magnetostratigraphy of sedimentary successions, and I'll describe that first of all. I estimate that probably about 90% of expeditions are the magnetics team are really focusing on that. But it's also possible to use paleomagnetism to understand tectonics. I'll give you some examples of that, to reorientate cores that are originally unoriented. And then finally on this list, it's often an overlooked topic of magnetic anisotropy, which can give you some really good insights into processes that are affecting the rocks that you're sampling, the rocks or sediments that you're sampling. So I'll give you some examples of each of these. My examples are going to be drawn from mainly JR type expeditions, but as I've just pointed out, the techniques are the same regardless of whether you're doing an MSP. I've not sailed on an MSP, so my examples mainly come from JR type expeditions. So magnetostratigraphy, first of all, well, you're all aware of these sorts of diagrams, I'm sure, arises from the fact that the Earth's magnetic field reverses its polarity periodically in a sort of non-systematic way, and that builds up the polarity timescale that we can use to date sedimentary successions, for instance. What I'm not going to talk about today is the sort of objectives for IODP that you can have to understand crustal magnetism and the signal from marine magnetic anomalies. That's a topic that's beyond what I can cover in a short 30-minute presentation. So the first example I'll give you is from IODP Expedition 351, which is one of the expeditions a few years ago that went to the Izubonin Mariana Arc. It's located, the site drilled the expedition drilled some holes in the Philippine Sea at this location here in the Imami Sankaku Basin. And this is a schematic representation of what was recovered in a sort of 1,600 meter hole eventually into basement. It penetrated through a sequence of fairly coarse-grained sediments, which reflect the growth and death of a volcanic arc system, and then a transition then into more normal marine sedimentation as we get closer to the present day. And I'll give you 2 examples in my talk today that come from this, but I'm going to first of all talk about the magnetostratigraphy, which even in these relatively coarse sediments was possible to achieve. So this is mainly based though on the analysis of the archive half cores, which are passed through those magnetometers that I showed you at the beginning. So here's an example from part of the top sort of 200 meters of hole U1438B on this expedition, giving you an idea of the density of data that can be produced using pass-through systems on sedimentary cores. So these data in the 2 graphs here, one is the inclination of the magnetic field, that's the dip of the magnetization in the rock, and then the declination is the angle from north. These data have been reoriented using a reorientation tool called a Flexit tool that will work with piston cores. And these cores were analyzed every 2 centimeters. So for anyone who's done any paleomagnetism in here, every one of these 2 little dots here has a demagnetization diagram attached to it. So you can see that there's an immense amount of data possible to achieve. So what you can see in this record is that the red line here, the red dashed line, is the expected values for a normal or reverse magnetic field in terms of the inclination. The declinations you would expect to be around north or 180 for normal and reversely magnetized rocks. And you can see that the directions are flipping backwards and forwards in both inclination and declination space, recording the reversals of the field that have been happening through time. So this is a wider, more detailed view of that. So how does this work? Well, taking those records, the shipboard or shore-based paleomagnetists would then define a reversal sequence for the sections that have been measured. So identifying where reversals have taken place, and then attempting to match that up to the known geomagnetic polarity timescale, which is itself refined using IODP data quite extensively. So you can see in this record that most of the reversals in the formal record of reversals in the black bars here have been picked out in this core section, allowing the section to be dated to a great deal of accuracy. Well, the whole data from this expedition for the magnetostratigraphy allows you to plot a graph of the depth against age. So that's your age model. And you can see each of these dots is a reversal that's been identified in the magnetostratigraphy. And you can see that the gradient of this basically gives you the sedimentation rate, which is plotted at the bottom, and that has varied through time. So the arc system formed sometime in the Eocene here, and then a lot of these sedimentary successions were being shed off those volcanic arc volcanoes into the basin in a period of rapid deposition. And then that arc died at around about 25 million years ago, and then we went to sort of normal pelagic sedimentation. And the change in gradient here is to do with compaction. I'll come back to that later on when I talk about magnetic fabrics. So of course, paleomag is one way in which you're going to get the age model for your sedimentary successions that you might drill through. The other is biostratigraphy. And this wider diagram on the right-hand side here shows the biostratigraphic constraints. A lot of the samples here were barren of microfossils, but this technique really came into its own at deeper levels, where it was able to provide data beyond the magnetostratigraphic record. So it's a combination of biostratigraphy and paleomagnetism that's going to give you your age model to establish what you've actually sampled. In there, I haven't talked about some other magnetic methods, things like using magnetic methods to develop a chronostratigraphy, or to work on U-channel samples that use sedimentary paleointensity to date sediment. So those are also techniques that are possible. So if we move up now on to the tectonic sort of settings, this can range from very straightforward applications of paleomagnetism, like again, this is in the Philippine Sea from an ODP expedition, leg 195, where the variation of inclination with latitude is well known, and therefore you can invert the inclination in your sediments to recover the paleolatitude. So in this case, this record from this hole was documenting the northward movement through time of the Philippine sea plate relative to the rotation axis of the Earth. It can also be used for looking at local tectonics as well, and I'll give you a couple of brief examples. This one comes from the Atlantis Bank Oceanic Core Complex on the Southwest Indian Ridge, which is one of these large mountainous sort of massifs on the seafloor formed by detachment faulting. This has been studied by a number of expeditions, including one of the deepest holes ever drilled at 735B. I'm going to show you some data from this one from U1473 from Expedition 360. And what we're really interested in here is whether the basement rocks have been rotated during their evolution. This was an extraordinary expedition recovering a really special record of lower crustal gabbros, including one of the longest continuous pieces of rock ever drilled hard rock ever drilled by IODP. So here again is a record of inclination against depth through these holes. And what you can see on this diagram is that the dashed line represents the expected inclination at this site, and all of the data from these gabbros have got inclinations which are steeper than that, and therefore they've been tectonically rotated away from the expected direction. Now, with non-oriented cores, it's actually quite difficult to deal with rotation data. So what you have to deal with in this sort of circumstance is to take the expected inclination and then figure out what it would do if it was rotated around a various axes. These are around various trends of a tilt axis. This one's ridge parallel to about 30 degrees away, taking into account various plunges. So you can work out theoretically what would happen to a reference direction, compare it with your observed inclination, and then put some constraints on the likely rotation that's happened. And from these two holes, this is the hole drilled up on Expedition 360 and the earlier one at 735B. You can see there's a real difference, a significant difference in the amount of rotation recorded. So in this particular case, what's happened is that the rotation is smallest closest to the ridge and greater as you move away from the ridge. So that's consistent with what we call a detachment mode of seafloor spreading. I'll come back to that in a moment or two with another example. So I mentioned there that cores are coming up. We're sort of hamstrung as paleomagnetists because we don't have the full core orientation normally. There are two ways in which cores can be reoriented. One is just use the direction of magnetization and rotate that back to north or south, depending on its polarity, and use that to reorient your core. Or you can do it independently, which is a much more lengthy process. So here's an example from an expedition from expedition 304 to Atlantis Massif in the Atlantic Ocean. And you can see the problem here. These pieces of gabbro coming up in the core liner we know the way up, but we don't know which way round they are in terms of where a north arrow would be on these. So the data I'm going to show you come from Atlantis Massif, which is another of these core complexes formed by detachment faulting on the seafloor in slow and ultra slow spreading systems. Well, here what we can do is adopt a different approach to reorienting core, where you try to match up structures in the core with structures that are seen on borehole images collected during the wireline logging operations. And in particular, this is using a tool called the Formation Microscanner, which is a wireline tool based on resistivity, where these little pads on the end of this tool pop out and touch the borehole wall, measuring the sort of micro resistivity using this pad of electrodes. And that gives you an image like the one you see over here, with areas that are conductive being in dark brown, areas that are more resistive in light brown. And further up on this wireline string, there's a 3-axis magnetometer that orients the tool, and therefore these images become oriented with respect to true north. And then if we can identify features like fractures in these images, a planar fracture would produce a sinusoidal path on these images. And we can work out from that sinusoid what the dip direction is and what the dip angle is from the height of the sinusoid. So if we can get that data down the hole from the borehole wall and match it up with structural data from the core, then you can potentially find unique matches that allow you to reorient your core back to the correct reference frame. Well, that's what we did in Expedition 304, 305. Some examples here on a StereoNet. These dots here that are widely scattered are in the core reference frame, okay, in both of these cases. And the distribution here is due to the pieces rotating in the core barrel. And when we adopt this core log integration approach, we can reorient those and get nicely clustered directions of magnetization that then allow us to work out the amount of rotation that's happened. In this case, about 45 degrees of tilting occurred during the evolution of these rocks. And that's consistent with this sort of rolling hinge model for oceanic detachment faults, which involves a fault initiating at quite a steep angle and then rolling over isostatically as it unroofs and flexurally as it unroofs, so that you end up with these curved fault traces with time. So the rocks that we sample over here have been rotated relative to their original positions. So here, that evidence like the one I just showed you led to a sort of definition of a new mode of seafloor spreading back in 2011, which is called detachment mode seafloor spreading, where these large lithospheric scale detachment faults unroof lower crustal and upper mantle rocks onto the seafloor and basically take up plate extension at times when magmatic activity is at a low. And we've extended this work now across a number of oceanic core complexes with different authors and also into ophiolites. And this seems to be a sort of characteristic feature of these oceanic core complex systems, both in the modern oceans and in ophiolites, with rotation around the low angle axes that are parallel to the strike of the ridge. Okay, I want to finish by showing you some examples of this final topic, magnetic fabric analysis, which is something that some people have heard of, many people are not familiar with. And this is possible to measure on board ships, but it's actually much better to measure this back in a lab like the one in Bremen, where you're not suffering from having a large moving magnetic ship around you while you're trying to do sensitive magnetic measurements. So some of you may have heard of this technique before, anisotropy of magnetic susceptibility, or AMS for short. let's take that a little bit at a time. Susceptibility is the parameter that relates the magnetization you get in a material to the field that's been applied to the material. So susceptibility in this equation is this symbol K. And different materials behave differently in different magnetic fields. So some minerals that have got no real iron in their chemistry have what's called a diamagnetic response, which is a very weak magnetic response. Others like pyroxenes, olivines, hornblendes, which have iron in their structure, have what's called a paramagnetic response, which is much stronger than this. Okay, so as you apply a magnetic field, the magnetization gets larger, and the gradient of this line is the susceptibility. And then the most important minerals that we have in magnetism are the ferromagnetic minerals like magnetite. And these don't have a simple relationship like this. They have this sort of hysteresis loop, but there is a linear relationship at very low fields. So strictly, we should call this anisotropy of low field susceptibility. Well, these sorts of diagrams give you the impression that susceptibility is a constant, but actually it varies depending on which direction you measure it in. And that gives rise to a susceptibility ellipsoid defined by maximum, intermediate, and minimum axes of susceptibility, easily measured using susceptibility bridges that are available on the ship and in almost every paleomagnetic lab in the world. So what causes this anisotropy, this variation in susceptibility with direction? It can be one of three different things, really. It can be a preferred orientation of the crystallographic axes of minerals, for instance, in crystalline igneous rocks. It can be due to the shape preferred orientation of grains. That's particularly true for magnetite-rich rocks. Or it can be due to distribution of grains which are themselves perhaps isotropic, but interact with each other to produce what's called a distribution anisotropy. So I'll go back to the IBM expedition for the first example here. So in this topmost unit sampled on this expedition, there was just a sequence of really quite uniform and monotonous pelagic muds. This is what they look like. The core description team, which actually on this expedition was consisted mainly of igneous petrologists, were having great fun finding new ways of describing these. But this is some anisotropy data that we published from these rather monotonous and boring looking sediments at the top of the section, which no one else was really that interested in. And what you can see here is a number of graphs. This one is the amount of anisotropy, so the strength of the fabric. And this is the type of shape of the anisotropy. Prolate means sort of cigar shaped, elongate, and oblate means flattened, like a pancake. And what you can see is that the anisotropy degree in the topmost section, down to about 80 meters below the sea floor, is almost non-existent, very, very low anisotropy. And then it gradually increases once we cross over this, and then after that, it remains fairly constant down the hole. And that's reflected in this shape as well, in that the shapes are widely varying and not very well developed down to this limit. And then they suddenly become very flattened and oblate. So this is a magnetic record of the development of bedding fabrics in these sediments. They're basically soft and fluffy with very little sedimentary structure up here, and then get compacted and produce a flattened fabric down here. So this is what that looks like on a stereonet. If you're interested in stereonets, above this 83-meter level, the axes are broadly sedimentary. You'd expect a minimum axis perpendicular to the bedding, or to the along the axis of the hole in these sorts of environments, and fairly random. And then we go below 83 meters, and suddenly you get a perfect sedimentary fabric forming. So if you combine that with the age constraints I showed you in the magnetostratigraphy, then you can sort of date the timing of bedding fabric development in pelagic sediments. And in this particular example, it took about 6 million years after deposition for these rocks to start to develop what you might recognize as bedding related fabrics that you can start to pick out and see. I'll finish by just giving you two very quick examples of how these sorts of techniques can be applied to hard rocks. Here we see Damon in his natural environment on the quayside, about to board the JOIDES Resolution. So the first example comes from a series of expeditions that he led to the Cocos Plate and hole 1256D, which was sampling through a complete section of oceanic crust and has reached the Gabbros for the first time. In doing so, it passed through a sheeted dike complex, and there was a very interesting paper by Peloso and others in 2013, where drawing on a combination of analyses of the FMS images to give you the sheeted dike orientations in a true reference frame and the anisotropy, you can see that in the core reference frame, these fabrics are fairly random. But when you reorient them using the remnants directions, the maximum axes in this case of susceptibility are, which is these blue squares, are parallel to the strike of the sheeted dikes that have been sampled, giving really great evidence for there being a long axis flow of magma during the formation of the sheeted dike complex. So many people think of dike complexes as things that just come up from below, but actually in this particular case, and many others in ophelites as well, we can demonstrate that actually flow in sheeted dike complexes often involves a lateral movement of magma. And then just the final one, which is an example from Expedition 360 sampling gabbros, where we have basically the opposite type of fabric occurring. These are gabbroic samples which have got fairly low angles of the maximum axes throughout the core. When you reorient those using the magnetism, you end up with a cluster of axes, which is basically along a flow line in both of these holes. So this is recording the magmatic flow in the lower crust during seafloor spreading away from the ridge crest. Okay, I'll stop there. Thank you very much.
Okay, thank you very much, Tony. Nice to see Costa Rica. Any questions for Tony? I mean, for many of us, you know, well, certainly I, you know, was educated in a department that didn't have at the time any paleomagnetism, and really you know, I think there's been this huge resurgence in the uses of paleomagnetism over the last 20 or 30 years, principally due to its application in scientific ocean drilling. So it's sort of recreated a whole new earth science domain, reinvigorated it.
Mm. Yeah, certainly there's a two-way benefit there in that, you know, we use the magnetic polarity timescale to date samples that we're collecting, but in doing so, we actually help to refine that timescale. So that's shouldn't be underestimated that actually IODP and its predecessors have been largely responsible for getting this, getting the real details of the magnetostratigraphy that we look at. So the question there is magnetostratigraphy done as standard on all IODP expeditions? Well, magnetic measurements are done on them all. If you pass through a sedimentary succession, then magnetostratigraphy is the main task of the paleomagnetists, to be able to help to date those rocks. If it's a hard rock expedition where the sediments are not necessarily sampled well, for instance, if you're doing rotary drilling into hard rock, then the sedimentary successions you pass through just get churned up. But in those circumstances where we've got a hard rock focus, then yes, there are routine IODP paleomagnetic measurements made on them. So all sample materials are measured. And it's done two ways. One is to do what I showed you before, which is to analyze and demagnetize the archive half section, which gives those sorts of continuous measurements. And the other is on discrete samples, which I didn't really show you today, but basically you could take a small plug out the working half of the core and analyze that in the lab, either post-cruise or on board the ship. So yes, it is done as a standard on all expeditions, but not always. It's not always magnetostratigraphy.
Yeah, and I'd just to add to that, I mean, even in particularly expeditions where we're interested in the aging of the ocean crust and how you know, interactions between the oceans and the ocean crust affect global chemical cycles. You know, the rate of sedimentation and the rate of burial of the basement topography is one of the key things we need to understand. And actually seeing how those sedimentation rates and that time scale is built up through the combination of micropaleontology and magnetics is actually really fascinating. I had one other question, and that was about the integration with the wireline logs.
Mm-hmm.
I mean, you talked about FMS, but all these cores also get measured on continuously for magnetic susceptibility, but also that measurement is made downhole as well. Yeah,
that's right. So that can help you in, for instance, in areas where you've got intervals of no recovery, for instance, or low recovery, and you've got a continuous record of susceptibility down the hole from a wireline log. Then you can play around with sort of shifting core sections up to try and match up with the susceptibility record. There's a whole host of ways in which you can integrate core measurements with wireline measurements. I think it's really essential that's tried on all expeditions, really. And certainly there have been big examples where where large intervals of non-recovery, we managed to get really good information about what's going on from the wireline logging. So yeah, so the susceptibility measurements are made on a multi-sensor track system, and that's measured on all expeditions. And what we encourage people to do is to set the measurement interval for that to be some multiple of what you're measuring in the Paleomag lab, so you get absolute correspondence between the points on the two different systems. And the susceptibility alone can be giving you all sorts of information. It principally is controlled by the concentration of magnetic minerals in the section. So for instance, if you're sampling a series of sediments that have got tephra layers in them or ash layers in them, those will often stand out as big spikes in susceptibility and picked up by the physical properties specialist on board the ship or back in the lab in Bremen. Another question from Tom: is there any development of other downhole magnetic measurements of remnants, etc.? Well, as Damon mentioned, wireline logging tools have really good susceptibility tools on them. There have been attempts to play around with putting 3-axis borehole magnetometers down holes, and then being able to then invert that data to get the remnants direction of the borehole wall precisely, well, not precisely, but directly. Those have been really not very successful, really. On Expedition 351, we had a student coming out from a lab in Germany, which is developing one of these things, and managed to sort of test it once or twice, but it didn't really work very well. But in the future, we hope that, you know, proper downhole magnetometers might be able to give you some information about the borehole wall. The problem is that you've also got all sorts of other stuff going up and down in the hole. You know, you've got wire, you might have near the top, you'll have casing, etc. So logging is always a bit of a tricky issue from a magnetic perspective.
Yeah, Tony, one thing you might want to just mention is about induced magnetism from the drill string or the drill bits or the core barrels.
Yeah.
And how that's dealt with. Yeah.
So this is a really important point, actually. That well, firstly, something I didn't mention earlier on is that your ability to do magnetostratigraphy in particular is really controlled by what latitude you're drilling at. So if you're close to the equator and you don't have oriented cores, then telling a normal from a reverse direction is very difficult because the inclinations are so shallow, they look very similar to each other. But there's also this issue of having what's called a drilling induced magnetization that sits on top of the natural signal in these samples. And this basically comes from the fact that you're taking these materials and you're passing them through a really high magnetic field at the end of the drill barrel where the drill bit is, or where the coring shoe is. And there's a really high magnetic field around that. And also the mechanical vibration that happens can also help to induce a magnetization. So in some special circumstances, in quite a lot of cases, you end up with a really quite strong overprint on the direction of magnetization, which points down the hole and has to be removed by demagnetization before you recover the real signal beneath. Now, in most cases where people are sampling sediments, that's not really a major issue. And if you're only particularly interested in the magnetostratigraphy, then you really just need to know when it's gone from reverse to normal. And that's fairly easy to see through. But in hard rocks, it can be very difficult. And sometimes you end up with nothing but this drilling induced magnetization. Unfortunately, it's something that you can't predict in advance. So you never know what you're going to get until you start measuring. And not all of the sequence you sample might be affected in that way. So it can be fairly hit and miss whether your samples are going to be badly affected or not. Best to get over that by doing analyses onshore when you get home on the discrete samples, which can then be conducted in a much more controlled environment.
Yeah, I mean, there have been suggestions of titanium drill bits and titanium drill strings, but they're probably prohibitively expensive.
I don't think that would get over the mechanical problems. You know, you can get shock-induced magnetizations as well. So,
right. Okay, in some ways it's remarkable it works at all.
It's magic.
Okay, thank you. Thank you very much, Tony.